On December 31st, something changed. Not visibly, not dramatically. The sun looked the same as it always does, a steady disk of light against the morning sky. But instruments scattered across the globe began registering something unusual. A signature in the solar wind, a ripple in Earth's magnetic field, numbers climbing where they shouldn't. Within hours, engineers at power stations noticed voltage fluctuations. Satellite operators saw trajectories drift by fractions of a degree. Radio operators lost contact with aircraft over polar routes, small disruptions, isolated incidents, the kind of technical hiccups that get logged, investigated, and usually explained away. But this time, the pattern was different, because 93 million miles away, the sun had done something it doesn't do often, something we've only witnessed a handful of times in the entire history of modern astronomy. It had released a coronal mass ejection so powerful, so perfectly aimed, that scientists immediately began calculating not if it would hit us, but what would happen when it did. This is the story of that event, and what it revealed about the fragile thread connecting our civilization to a star we still don't fully understand. If you're here for a deeper look at the universe, one that goes beyond headlines and into the actual science of what's happening above us, you're in the right place. This channel exists to explore cosmic events with the rigor they deserve, while keeping things clear enough to follow whether you're just winding down for the night or genuinely curious about how solar physics shapes our daily lives. If that resonates with you, consider subscribing. And if you want to catch future videos on rare astronomical events as they happen, notifications help make sure you don't miss them. No pressure. Just an invitation if this kind of content brings you value. The sun doesn't have weather the way Earth does. It has something far stranger. When we talk about storms on our planet, we're describing air masses colliding, moisture condensing, pressure systems shifting. Predictable physics playing out in an atmosphere we understand reasonably well. But the sun has no solid surface to anchor these processes. No clear boundary between inside and outside. What we see as the solar disk, that sharp golden circle in the sky, is just the layer where light finally escapes after spending thousands of years bouncing around in the star's interior. Everything above that visible layer is atmosphere, except this atmosphere doesn't behave like ours. It gets hotter as you move away from the surface. The visible photosphere sits around 5,500 degrees Celsius, reasonable enough for a star. But climb upward into the corona, the ghostly halo you can only see during a total eclipse, and temperatures spike to over 1 million degrees. Heat flowing the wrong direction, energy concentrating where it should be dissipating. Scientists have known about this temperature inversion for nearly a century. They still don't fully understand why it happens. This is where solar storms are born, not in the dense nuclear furnace at the sun's core, but in this strange outer realm where magnetic fields become more important than gravity, where plasma moves not because of heat or pressure, but because of invisible lines of force threading through space. And those magnetic field lines, they're not static. The sun rotates, but not like a solid object. The equator spins faster than the poles, completing a full rotation in about 25 days while the polar regions take 35. This differential rotation twists the magnetic fields like rubber bands being wound tighter and tighter. Over days, weeks, months, these fields build tension. They loop through the solar atmosphere in elegant arcs, each one channeling plasma along its length, holding back enormous reservoirs of energy. Most of the time, this system holds, the fields stay organized, the plasma flows along predictable paths, the sun appears stable, but magnetic fields have a breaking point. When the tension becomes too great, the field lines don't just bend, they snap. They reconnect in violent, explosive reconfigurations that release energy equivalent to billions of nuclear weapons in seconds. The plasma that was being held in place suddenly has nothing constraining it. It erupts outward at speeds that seem impossible for something with that much mass. This is a coronal mass ejection, not a burst of light or radiation, though those often accompany it, a physical thing, a billion-ton cloud of magnetized plasma hurled into space at millions of kilometers per hour. And here's what makes them particularly dangerous. They're directional. Unlike solar flares, which radiate energy in all directions like a flashbulb, coronal mass ejections are aimed. The magnetic reconnection launches them along specific trajectories determined by the geometry of the field lines at the moment of breaking. Most shoot off into empty space, missing every planet in the solar system. Some graze Mercury, others head toward the outer planets where they'll dissipate long before reaching anything significant. But occasionally, purely by chance, one launches directly toward Earth. The event on December 31st was one of these, not because the sun targeted us, not because some cosmic alignment made it inevitable, simply because at the exact moment those particular field lines reconnected, Earth happened to be in the path. What makes this architecture invisible is that we can't see magnetic fields directly. We infer them. Spacecraft measure the charged particles they guide. Telescopes track the light emitted by plasma flowing along them. Computer models reconstruct their shapes based on observations of the photosphere below. But the actual moment of reconnection, the instant when stability tips into catastrophe, that happens too quickly, in structures too small for our instruments to capture in real time. We see the build-up. We see the aftermath. The critical transition remains hidden, which means every coronal mass ejection teaches us something we didn't know before. Every eruption reveals some detail about magnetic field behavior that our models hadn't predicted. The sun has been doing this for 4.6 billion years. We've been watching with modern instruments for barely 50. We're still learning the rules of a game that was already in progress long before we arrived. And the December 31st event? It followed those rules in ways that caught even veteran solar physicists off guard. Because while the fundamental mechanism was familiar, magnetic reconnection, plasma eruption, directional launch, the scale and timing suggested something unusual about the field configuration that preceded it. Something that wouldn't become clear until we looked more carefully at what had been building beneath the surface in the days before the eruption. The sun has patterns. We've mapped them, catalogued them, built entire fields of study around predicting them. An 11-year cycle of magnetic activity, rising from quiet minimum to turbulent maximum and back again. Sunspot numbers that correlate with solar storm frequency. Active regions that develop, persist for weeks, then fade as the rotation carries them out of view. These patterns give us comfort. They suggest the sun is knowable, manageable even. And then it does something that doesn't fit. On December 26th, 5 days before the eruption, a sunspot group appeared on the eastern limb of the solar disk. Standard procedure. Active regions rotate into view from the far side of the sun constantly. Observatories logged it, assigned it a designation, and began tracking its magnetic field configuration. Nothing about it seemed unusual at first. The sunspots were moderately sized. Their magnetic polarity followed the expected pattern for this phase of the solar cycle. Leading spots with one polarity, trailing spots with the opposite, separated by neutral lines where the field direction reversed. Classical bipolar structure, the kind that appears hundreds of times throughout a solar maximum. But over the next 48 hours, something changed. The neutral line between the leading and trailing spots began to compress. Not gradually, as you'd expect from normal evolution, but rapidly, magnetic flux piling up along a narrowing boundary like traffic converging on a closing lane. By December 28th, instruments measuring the magnetic field strength along that line were registering values twice as high as the initial observations. This kind of compression stores energy, a lot of it. Magnetic field strength scales with energy density in a very specific way. Double the field strength, and you've quadrupled the energy stored in that volume. The compression happening in this active region wasn't just concentrating the field, it was building a reservoir of magnetic energy dense enough to power something catastrophic if it released suddenly. Solar physicists noticed. They upgraded the region's flare probability forecast. They flagged it for enhanced monitoring. But here's the problem. Compressed neutral lines appear frequently. Most of them release their energy gradually through smaller eruptions, C-class flares, minor plasma ejections that barely register when they reach Earth. The vast majority never produce anything globally significant. Predicting which ones will escalate is still more art than science. The models look at shear along the neutral line, how much the magnetic field twists horizontally as it crosses the boundary. They examine the angle of the field's emergence from below the surface. They calculate something called the free magnetic energy, which represents how far the actual field configuration has deviated from the lowest energy state it could theoretically relax into. All useful metrics, none of them definitive, because the sun doesn't erupt on a schedule. It doesn't follow thresholds where once a magnetic field reaches X strength or Y shear, reconnection automatically triggers. The mechanism is fundamentally chaotic, sensitive to tiny variations in field geometry, to plasma flows we can't measure directly, to instabilities that develop faster than our instruments can refresh their observations. The December 26th active region checked all the warning boxes: high magnetic flux, significant shear, rapid energy accumulation. But so had dozens of other regions earlier that year that never produced anything noteworthy, until December 30th, when the configuration changed again. A new magnetic flux emergence appeared, not in the main sunspot group, but just to its west. A smaller bipolar region, individually unremarkable, except for one detail. Its magnetic orientation was rotated relative to the larger structure, not aligned, not opposed, tilted at an angle that created a three-way intersection of field lines from three different sources. Magnetic field topology matters enormously in reconnection physics. Two-dimensional models, the kind that treat field lines as simple loops emerging and returning to the surface, predict relatively benign behavior. But add a third dimension, introduce field lines intersecting at angles, and the system becomes what physicists call topologically complex. In these configurations, reconnection can cascade. One set of field lines reconnects, which destabilizes an adjacent set, which triggers reconnection elsewhere, which feeds back into the original site, a chain reaction constrained only by how much energy is available in the surrounding field. Nobody predicted this flux emergence. It appeared between observation windows, too small to see on the sun's far side, only becoming visible once rotation brought it into Earth-facing view. By the time solar physicists recognized what was developing, the three-way intersection had already formed. 18 hours later, the field line snapped. Not gradually, not with warning flares building in intensity. The reconnection initiated deep in the corona, at an altitude where plasma density is low but magnetic field strength remains high, the optimal configuration for launching material rather than just releasing radiation. Instruments on the Solar Dynamics Observatory captured the eruption in multiple wavelengths simultaneously. Ultraviolet channels showed the plasma brightening instantly across thousands of kilometers. Magnetogram data revealed the field lines reconfiguring in real time, loops that had arched gracefully through the corona suddenly whipping outward like released springs. And then the material started moving, at first just the plasma directly involved in the reconnection. But coronal mass ejections don't work like explosions in air, where a shockwave expands spherically from a point. The erupting plasma carries its own magnetic field, stretched and distorted versions of the field lines that were holding it before reconnection. As this magnetized cloud accelerates upward, it drags surrounding material with it, not through friction but through magnetic coupling. The eruption grew. What started as a localized reconnection event became a massive expanding bubble of plasma and magnetic field, lifting away from the sun and accelerating outward. By the time it cleared the corona and entered interplanetary space, it carried more than 1 billion tons of material, and it was aimed almost perfectly at Earth. Not because of anything special about our position, not because the magnetic geometry knew where we were, simply because the three-dimensional orientation of those intersecting field lines at that particular moment happened to point them in our direction. Pure geometric coincidence. The kind the sun produces randomly, indifferently, without regard for what might be in the path. But here's what made the December 31st event unusual: the speed. Most coronal mass ejections travel at 300 to 500 kilometers per second, fast by terrestrial standards, but slow enough to reach Earth in 3 to 5 days. The extra time gives forecasters room to issue warnings, power companies opportunities to adjust grid operations, satellite operators chances to put spacecraft into protective modes. This one left the sun at 2,100 kilometers per second, 4 times the typical speed. Fast enough to cross the distance to Earth not in days, but in just over 40 hours. Fast enough that many of the standard preparation protocols, designed around multi-day warning windows, would become almost useless. And fast enough that when it hit, the impact would carry significantly more kinetic energy than slower events, compressing Earth's magnetosphere in ways that don't happen during ordinary geomagnetic storms. The sun had forgotten to behave predictably, or perhaps, more accurately, it had reminded us that our patterns are observations, not laws, that the 11-year cycle describes average behavior, not constraints, that an active region following all the classical development rules can still produce something exceptional if the right invisible conditions align. By the time observatories confirmed the trajectory and calculated the arrival time, there were 38 hours remaining. Enough time to warn the world, not quite enough time to prepare it. Space is not empty. We imagine it that way. Vast darkness between planets, a vacuum so complete that sound cannot travel and matter exists only in isolated pockets around stars and worlds. But the region between the sun and Earth is filled with something we can't see and rarely think about. The solar wind. It flows outward from the sun constantly, in all directions, at roughly 400 kilometers per second. Not a metaphorical wind. An actual stream of charged particles, electrons and protons stripped from hydrogen atoms in the sun's corona, accelerated to such high speeds that they escape the star's gravity entirely and rush out into interplanetary space. This wind has been blowing for billions of years. It fills the solar system out to a boundary more than 100 times Earth's distance from the sun, where it finally collides with the interstellar medium and stalls. Everything inside that boundary, all the planets, moons, asteroids, comets, and spacecraft we've ever launched, exists inside the sun's extended atmosphere. We orbit within our star. The solar wind carries the sun's magnetic field with it, not as separate entities, but woven together. The field embedded in the plasma constrained by the field, both moving as a coupled system. As the sun rotates, this field gets dragged into a spiral pattern, like water streaming from a rotating sprinkler. By the time the wind reaches Earth, the magnetic field lines aren't pointing radially outward from the sun anymore. They're curved, angled, shaped by rotation into what astronomers call the Parker spiral. Under normal conditions, this system is relatively stable. The wind flows smoothly. The magnetic field varies in strength and orientation but changes gradually. Earth's magnetosphere, our planet's own magnetic bubble, deflects most of it harmlessly around us. But a coronal mass ejection doesn't flow smoothly. It punches through the existing solar wind like a freight train crashing through fog. The billion-ton plasma cloud, carrying its own twisted magnetic field, moves more than 5 times faster than the ambient wind surrounding it. And when something moves faster than the medium it's travelling through can get out of the way, physics has a name for what happens next. A shockwave forms, not a sound wave. There's no air to compress. A magnetohydrodynamic shock, where the magnetic field and plasma compress together into a steep gradient of density, velocity, and field strength. The leading edge of the coronal mass ejection pushes aside the slow-moving solar wind ahead of it, piling up material and field into a thin, intense boundary layer. This shockwave travels ahead of the main plasma cloud. It reaches Earth first, a precursor impact that compresses the magnetosphere, agitates the radiation belts, and sends the first surge of energetic particles cascading into our upper atmosphere. But the shock is just the warning shot. Behind it, separated by thousands of kilometers, comes the actual magnetic structure, the erupted field lines from the sun's corona, still carrying their original topology but stretched and distorted by the journey through interplanetary space. This is what physicists call the magnetic cloud, and its properties determine how severely Earth's magnetosphere will be affected. Because here's what most people don't realise about geomagnetic storms. It's not the mass of the plasma that matters most. It's the orientation of the magnetic field it carries. Earth's magnetic field points northward in interplanetary space, emerging from the south geographic pole, looping through space, and returning at the North Pole. When a coronal mass ejection arrives carrying a magnetic field pointed in the same direction, the two fields simply press against each other. They don't connect. The interaction is relatively gentle, and most of the plasma cloud flows around Earth's magnetosphere without penetrating it. But if the coronal mass ejection's magnetic field points southward, opposite to Earth's field, something very different happens: magnetic reconnection. The same mechanism that launched the eruption from the Sun now occurs again in near-Earth space, at the boundary between the planetary magnetosphere and the incoming solar plasma. Field lines from Earth connect with field lines from the Sun, and in doing so, they open doorways through which solar wind particles can flow directly into our magnetosphere. This is how geomagnetic storms escalate from minor disturbances to global events, not just from the impact, but from the sustained injection of energy as long as that southward magnetic field persists. The problem with the December 31st event was that nobody could predict which direction the field would be pointing when it arrived. Coronal mass ejections are three-dimensional structures. The magnetic field inside them twists and rotates. As the cloud travels through space, its internal field can shift orientation, sometimes remaining stable in one direction for hours, sometimes rotating through multiple cycles during the journey. Spacecraft positioned between the Sun and Earth, particularly the Deep Space Climate Observatory, stationed 1.5 million kilometers upstream, can measure the field orientation about an hour before the cloud reaches our planet. 1 hour of warning, enough time to send alerts, not nearly enough time to implement most protective measures for infrastructure. And in this case, the rotation rate of the magnetic field suggested something worse. Data from the Solar and Heliospheric Observatory, watching the eruption leave the Sun, showed a highly twisted magnetic structure. Not a simple loop that had lifted away cleanly, but a writhing complex topology, evidence of that three-way field line intersection that had triggered the eruption. Such structures tend to be unstable during their journey, their internal fields reconfiguring in flight as different regions of the cloud move at slightly different speeds, shearing past each other. Forecasters call these complex ejecta. They're harder to model, harder to predict, and statistically more likely to include periods of strong southward field orientation somewhere in their structure. Even if the leading edge arrived with a benign field direction, the trailing portions might carry something dangerous. By New Year's Eve, the shockwave had already crossed Mars' orbit. Instruments there registered the passage, a sudden jump in magnetic field strength, a spike in energetic particle counts, then a return to waiting as the main cloud continued its journey inward. 31 hours to Earth. At Deep Space Climate Observatory's position, engineers verified that all instruments were functioning, that data links to ground stations were stable, that onboard memory had been cleared to store the high-resolution measurements they'd be collecting once the cloud arrived. This spacecraft would be humanity's only real-time view of what was coming. The only way to know, with certainty, whether the magnetic field orientation spelled disaster or merely inconvenience. And behind that spacecraft, closer to Earth, other systems were going on alert. Satellites in geosynchronous orbit, the communications and weather spacecraft that circle at exactly the same rate Earth rotates, hovering over fixed points on the equator, sit directly in the path where coronal mass ejections hit. They would experience the impact first, the most intensely, with no planetary magnetosphere to shield them. Power grid operators were reviewing contingency plans, not shutdown procedures. You can't turn off a continental electrical network on an hour's warning without causing more damage than the storm itself. But load balancing strategies, capacitor bank adjustments, decisions about which transformers could be temporarily disconnected if voltage swings became too extreme. Airlines were rerouting polar flights. The same magnetic field lines that channel solar particles into Earth's atmosphere near the poles also disrupt radio communications there and increase radiation exposure for crew and passengers. Any flight path crossing above 70 degrees latitude was being directed to lower, longer routes. And aurora photographers were heading north, because for all the danger a geomagnetic storm poses to technology, it also produces something undeniably beautiful. Charged particles spiraling down magnetic field lines into the upper atmosphere, colliding with oxygen and nitrogen atoms, exciting them to higher energy states that release light as they decay back down. Green curtains, red rays, purple edges, the sky on fire, visible far south of the Arctic Circle if the storm proved strong enough. 24 hours to impact. The plasma cloud, invisible except to specialized instruments, raced onward through the darkness, no deceleration, no course deviation, just inexorable motion along the trajectory set by that initial eruption geometry, 1 billion tons of magnetized matter crossing 3 million kilometers every hour, still carrying a magnetic field whose orientation wouldn't be measured until it was too late to do anything but watch what happened next. We talk about Earth's magnetosphere as if it were armor, a protective shell, a force field keeping harmful radiation at bay while we go about our lives on the surface, blissfully unaware of the cosmic bombardment happening overhead. And it does protect us. Without it, the solar wind would strip away our atmosphere over millions of years, leaving Earth as barren as Mars. The magnetosphere is why we have oceans, weather, breathable air, why life could evolve and persist. But it's not a solid barrier, it's not even close. The magnetosphere is a dynamic, constantly shifting region of space where Earth's magnetic field exerts influence over charged particles. It extends roughly 60,000 kilometers toward the Sun, 10 times Earth's radius. On the night side, the solar wind stretches it into a long tail that reaches beyond the Moon's orbit, a comet-like structure of magnetic field lines pulled downstream by the flow. This shape tells you something important. The magnetosphere isn't holding back the solar wind, it's being deformed by it. Under normal conditions, the pressure from the solar wind compresses the dayside magnetosphere while simultaneously stretching the night side into that extended tail. The boundary between them, called the magnetopause, represents the location where magnetic pressure from Earth exactly balances dynamic pressure from the incoming solar wind. Push harder from outside and the boundary moves inward. Reduce the pressure and it expands outward. Is not a wall, it's an equilibrium, and when a coronal mass ejection arrives, that equilibrium shatters. The first sign came at 1423 Universal Time on January 1st. Instruments aboard Deep Space Climate Observatory, still 1 million kilometers upstream, registered a sudden discontinuity in the solar wind. Density jumped by a factor of 20, velocity spiked. Magnetic field strength increased tenfold within seconds. The shockwave had arrived, 62 minutes to Earth. Data streamed back to ground stations, where automated systems processed it and forwarded alerts to agencies worldwide. Space Weather Prediction Center in Boulder, European Space Agency operations in Darmstadt, Space Environment Monitoring facilities in Japan, Australia, Canada, a coordinated observation network that had been waiting for this moment since the eruption was first detected. And then they saw the magnetic field orientation. Southward, strongly southward. Not just a minor deviation from northward, but a pronounced stable southward component measuring minus 25 nanoteslas. For reference, Earth's magnetic field at the surface measures around 50,000 nanoteslas. The interplanetary field is usually less than 10. A minus 25 nanotesla southward field represents an exceptionally strong geoeffective configuration, exactly the orientation most capable of driving severe geomagnetic activity, 58 minutes to impact. At geosynchronous orbit, satellites began detecting changes in their local space environment. Energetic particle counts rising. The outer electron radiation belt, a donut-shaped region of trapped high-energy particles surrounding Earth, started showing increased flux. Not from the shockwave yet, from particles accelerated ahead of it, surfing the compression wave like runners pushed by a gathering wave. Inside mission control rooms, engineers watched telemetry from dozens of spacecraft. Communication satellites, GPS constellation members, weather monitoring platforms, Earth observation systems, all of them about to experience conditions they were designed to survive but never designed to enjoy. Satellite electronics hate energetic particles. When a high-energy proton or electron strikes a sensitive transistor, it can deposit enough charge to flip bits in memory, trigger false commands, or in extreme cases, permanently damage components. Engineers call these single-event upsets, and they happen occasionally even during quiet space weather. During geomagnetic storms, they happen constantly. 51 minutes. The shockwave crossed lunar orbit. The Moon itself, lacking any magnetic field, experienced the impact directly. No atmospheric buffering, no magnetosphere deflection, just raw solar wind plasma striking the surface at 2,100 kilometers per second, implanting particles into lunar regolith, adding microscopic layers to the radiation-altered chemistry that makes moon dust so abrasive and clingy. If astronauts had been there, sheltering in habitats with radiation shielding measured in centimeters of aluminum and regolith, they would have needed to retreat to the most protected areas, not because the shockwave itself posed an immediate lethal threat, but because the energetic particle flux following it could accumulate to dangerous exposure levels over hours. Mars missions train for this. Lunar mission planners include it in habitat designs. The radiation environment in interplanetary space isn't optional to deal with. It's a fundamental constraint on human presence beyond Earth's protective magnetosphere. 42 minutes. Back at Deep Space Climate Observatory, instruments were now measuring the main body of the coronal mass ejection, the magnetic cloud following behind the shock, and the field orientation was holding steady, still southward, still strongly negative. This was the nightmare scenario, not a brief pulse of unfavourable field direction, but a sustained southward orientation that could last for hours. Every minute that southward field pressed against Earth's magnetosphere, magnetic reconnection would continue opening pathways for solar wind plasma to enter. Energy would accumulate. The magnetospheric system would be driven further from equilibrium. Ground-based magnetometers, instruments scattered across the planet measuring the strength and direction of Earth's magnetic field at the surface, were already showing preliminary disturbances, small deflections, a few nanoteslas here and there. The electromagnetic equivalent of ripples before a wave. 36 minutes. Power grid operators were on conference calls now, coordinating across regions. The electrical grid isn't a single unified system. It's an interconnected patchwork of generators, transmission lines, transformers, and substations, each managed by different utilities but all sharing power across regional boundaries. When one section experiences a problem, the stress propagates to neighbours. Geomagnetic storms create a specific type of stress the grid wasn't originally designed to handle. Earth's magnetic field changes during a storm. Not dramatically, we're talking variations of a few hundred nanoteslas at most. But those variations happen over large geographic areas, and according to Faraday's law of electromagnetic induction, a changing magnetic field induces electric currents in any conductor exposed to it, like 1,000-kilometre-long power transmission lines. These geomagnetically induced currents are different from the alternating current the grid normally carries. They're quasi-DC, flowing in one direction for minutes or hours at a time, determined by the rate and direction of magnetic field change overhead. And transformers, those crucial devices that step voltage up for efficient long-distance transmission and back down for safe distribution, were never designed to handle DC current. When DC flows through a transformer, it saturates the magnetic core. The transformer stops working efficiently, it draws excess current from the grid, it heats up, and if the saturation is severe enough, lasting long enough, the insulation inside can break down, leading to permanent failure. Replacing a large high-voltage transformer takes months, sometimes over a year. They're custom-built for specific installations, not kept in warehouses waiting for emergencies. Losing multiple transformers simultaneously across a regional grid could mean blackouts lasting not hours or days, but weeks or months. 28 minutes, airlines had successfully rerouted most polar flights, though a few were already in progress over northern Canada and Scandinavia when the alerts went out. Pilots were monitoring radiation dose rates and high-frequency radio communication quality. So far, both acceptable, but both would degrade rapidly once the main impact began. At ground-based radar installations near the Arctic, operators were seeing the first signs of ionospheric disturbance. Radio waves were refracting differently than normal, creating phantom echoes and range errors. Not enough to lose tracking entirely, but enough to require switching to backup systems and cross-referencing multiple sensors. 18 minutes. The shockwave was now close enough that its effects were propagating through Earth's magnetosphere ahead of direct impact. The bow shock, the permanent standing wave where the supersonic solar wind first encounters Earth's magnetic field, had moved inward by thousands of kilometres. The magnetopause compressed from its normal position at 10 Earth radii to less than 7. Earth's protective bubble was shrinking. And then, at 1525 universal time, the shockwave hit. Not with sound, not with light. With a sudden, violent compression of the entire magnetospheric system. Magnetic field lines on the dayside crushed inward. The bow shock lurched sunward, then rebounded. Waves of electromagnetic energy rippled through the magnetosphere at thousands of kilometres per second. At geosynchronous orbit, satellite sensors registered the passage instantly. Magnetic field strength doubled. Particle flux jumped 3 orders of magnitude. Spacecraft charging monitors, instruments measuring how much electrostatic charge builds up on exterior surfaces, showed values climbing into dangerous territory. On the ground, magnetometers swung sharply. Power grids experienced their first voltage fluctuations. Radio operators lost contact with aircraft. GPS receivers flickered as signals from satellites overhead became distorted, passing through the suddenly turbulent ionosphere. And this was just the shockwave. The main magnetic cloud, still carrying that sustained southward field, still packing the bulk of the erupted mass and energy, was still 30 minutes behind. The storm had begun, but the worst was yet to come. There's a peculiar irony to our vulnerability. The more technologically advanced we become, the more fragile we are to events happening 60,000 kilometres overhead. A century ago, a geomagnetic storm of this magnitude would have been nothing more than spectacular auroras and perhaps some disruption to telegraph lines. Inconvenient, but not civilization-threatening. Now we've built a world that runs on infrastructure exquisitely sensitive to things our ancestors never had to consider. The electrical grid, satellite navigation, high-frequency communications, precision timing signals, all of it depends on stable electromagnetic